Hello, my name is Scott Bortoff. I work at Mitsubishi Electric Research Labs in Cambridge, Massachusetts. And today I'm going to present some of our results on modeling contact and collisions for robotic assembly. So the primary motivation is to develop model-based control algorithms for this type of robot to put these types of parts into some sort of complex assembly. And we want a modeling framework, in other words, the mathematics and the software, to be consistent with the way we model robots and to be useful for model-based design. So that's an important point. We want to do more than just simulation. We want to use these models to design feedback controllers for assembly. So the model we're going to derive is basically a continuous time differential algebraic equation plus a finite state machine, which is very appropriate for Modelica. The implementation is completely in native Modelica, so we're not integrating different tools, and we can make use of the sophisticated solvers in the tools. The methods can be applied actually quite broadly, not just to robotics. So for example, in the center here we've got an elevator, which we've worked on, a model of an elevator where we're modeling the rope as a chain, and as the chain goes over this sheave, it comes into and out of contact. And other toys that we'll talk about later, like this ball maze. The ball, as it rolls through the maze, comes into and out of contact with these rings and these gates. So that's a good example also. So there's a lot of previous work in modeling contact and collisions. There's an awful lot of work that's come out of the computer graphics community in particular. The state of the art is to essentially represent the physics as a nonlinear or linear complementary problem. And to solve that, you basically solve a QP at each discrete time step. And so most of these tools will use a discrete time, typically first order discretization of the physics. So you get a discrete time model, and then at each step solve a QP. And so the real purpose of all this is just to compute solutions, primarily for animation. And that really doesn't meet our needs in terms of doing model-based control design. And so that's really why we're doing a lot of this work. I should mention that there's other work done in the Modelica community to integrate the Modelica language with some of these tools, in particular Gazebo. Gazebo is actually a very good tool, particularly with some of the newer solvers such as Dart, which is actually very similar to Modelica. So the basic method is that we want to extend the differential algebraic equation model that we've developed for this robot to handle contact and collisions. And so there's a lot of equations and noise on this slide, but essentially the bottom line is that the way we model this, which is a difficult system to model because it's a closed kinematic chain, and so the forward kinematics cannot be computed in closed form. However, we can model this as basically a high-index differential algebraic equation where we model each arm independently as an open chain and then model the holonomic constraint here as 6 algebraic equations. And you end up with a model that looks like this. So it's basically just a constrained Lagrangian type model. There are 24 equations and 24 states, which seems like a lot because this is just a system that has 3 degrees of freedom, so we would expect 6 equations. However, these equations are actually quite simple, and numerically it's very efficient to simulate in this way. And so we're going to take this representation and use it to represent contact physics. The trick is that we replace this constraint here, which makes the system index 3, with a linear combination of its first 2 derivatives. This is called Baumgartner's method of index reduction. This gives us an index 1 DAE. It's a completely mathematically correct model of this system. And we're going to take this framework and extend it a little bit so we can model contact and collisions. And so the basic result is summarized on the next 2 slides. So here's the same set of equations. And then if we notice, what we're going to do is this lambda, which is the Lagrange multiplier, if this is 0, then the objects that we're modeling here are free and not in contact. If this is positive, then the objects that we're modeling are actually in contact. And so this is essentially how we incorporate the complementary condition. It's the same thing. And when they're in contact, we're going to add this equation to the physics. And the key insight here is that this is a second-order differential equation that looks a lot like elastic collision. And so we're going to model the collision that occurs between two objects when they come in contact with this equation, tune the parameters here to capture the material physics. And what happens is when these come in contact, this gets simulated. These equations are linear second-order differential equations, and they will converge quickly to zero depending on the value of these two parameters. And so after the collision transient, this h, which represents the distance between these objects, converges exponentially to zero, and this enforces a penetration constraint after the collision transient is expired. Now, the other trick that we do sometimes is we add a stiff spring to this model, you could say. So we make it add this cubic term or higher order term. That essentially makes the collision stiffer. And after the collision transient has transpired, of course, this goes to zero. And so we can make this term smaller, the spring term, and that softens the constraint so we don't end up with a stiff system after the collision has transpired. So there are really two tricks. One is to use this constraint equation to model the elastic collision, and the other one is to add nonlinearity if you don't want this to be stiff after the collision. Now that's half the model. The other half is a finite state machine that we need to use to capture whether or not these two bodies or n bodies are in contact. And so the first idea is to just have a simple two-state machine. You're either free or you're in contact, and you switch when you come in contact, and you switch back to the free when this Lagrange multiplier changes sign. And the problem with this is this value h, which is the distance between objects, this is driven to zero by this constraint equation, and so you'll get chattering between these two states, which is very undesirable. And so we actually add a third state, basically a transition from contact back to free, and we call this state the ballistic state. It's probably a bad name, but in both the free state and the ballistic state, the Lagrange multiplier is set to zero, and the bodies are free to move independently. And then there's some switching here, switching criteria. So we basically switch out of this contact state to the ballistic state when the Lagrange multiplier changes sign. So in this state, actually this value of h, which again represents the distance between these objects, can either be positive or negative, depending on these tuning parameters here. And so we can switch back to this state if this passes through zero. So this is actually a well-posed finite state machine. You don't get any of these chattering characteristics. However, as we'll see, there is a negative consequence. So let's do an example, simple hello world bouncing ball example. Essentially, this is the simulation up here. We start the ball at 1 meter, and you can see it bounces. It's got a little bit of damping in this case. Every time it comes in contact, the Lagrange multiplier is active. It goes through all of these different contact states. So you see there's state 0, state 1, and state 2. That state we added is not a corner case. It's actually very important. And here's the code. So the code is essentially the algorithm block to represent the finite state machine, very straightforward and simple. And then the equation block to represent the differential algebraic equation. The key thing is that when we're in contact, we add this equation, which is the constraint stabilization equation. And when we're not in contact, we just set the Lagrange multiplier to zero. This is a completely legitimate Modelica code, and it compiles and runs just fine in the standard tools. Now, there is one problem with all of this. It's actually a minor problem, but interesting nonetheless. And that is if we set the damping to zero, then let's see what happens. We let our ball bounce, and if you look very closely over time, the position is increasing. And so we're adding energy to the system that's non-physical. And so why is that? And so the reason is that it has to do with the way we've designed this finite state machine. So basically, as the position comes back through zero, so the two parts are separate physically, the Lagrange multiplier is still positive, and that's just a consequence of the fact that we're simulating a DAE. As it, so between this time and the time it actually does pass through zero, we're actually adding non-physical energy back into the system. Now this is for a very short period of time, and frankly it's not that big a deal because it is a bit of a corner case to simulate something that doesn't have any damping. And by the way, I should add that a lot of these physics engines also fail to conserve energy in the same way, although we can explain exactly why this is if you analyze exactly what the Lagrange multiplier is doing. It's basically because we're adding back this gravity term, and that can act as a feed forward that avoids the penetration, any kind of penetration in the steady state. So that's good, but the negative consequence is that we have this little bit of non-conservation of energy. Okay, let's do a few examples. So the first example is this ball maze game. So the goal here is to get the ball into the center. The strategy, typically you sort of tip tilt this game to get the ball into the center, but we're actually going to do this a little differently. We're going to stand up the maze at an angle and then rotate it about its central axis to get the ball into the center. And that's actually has two positive things. One is now I just have 1 degree of freedom. The friction is better behaved, and in fact, you'll see that if I design a feedback, I actually make this problem quite simple. So what we're going to do is design a feedback controller that stabilizes this ball on the unstable ring using feedback, and then basically rotate the maze underneath the ball until it falls through all these gates into the center. So this is a good example because we have contact, then non-contact, then contact, then non-contact. It's the type of problem that this method's actually pretty good at handling. The dynamics are very straightforward. I won't go through that. There are two constraints when we're in contact. One of them is basically maintain the distance from the center, so stay that certain distance away. The other one is the rolling constraint, which is not so obvious, but basically this ball here has to roll against this ring when you're in contact. That's actually a holonomic constraint because this is just a one-dimensional problem in this case. The finite state machine is a little bit simplified here, so we just go from free to contact to free to contact. It's very simple. This actually works very well in simulation. You'll see that on the next slide. But this is an important point. We want to use this model for more than just simulation. We want to actually design a feedback controller to stabilize the maze against the ring. And so we can linearize this nonlinear model at this position here. When we linearize it, we can basically design two very simple lead compensators. First, to stabilize the ball. This is actually an open-loop unstable system, of course. And then the second is to stabilize the maze because there's a pole here at the origin. I won't go through the details. They're in the paper. The point is that this is a simple example of model-based control where we're using the dynamics to design the feedback based on the structure of the system. We get some results like some fundamental limits. There are lower and upper bounds on these two feedback gains. But the model tells us a lot about the mathematics, and we want to use the model, again, for this type of analysis and design beyond just simulation. Of course, it does simulate very well. So here's just a simulation where we start the ball outside the outer ring. It basically bounces through as we rotate the maze back and forth through all the gates and gets into the center. This is just a sequence of animations from the Dymola tool, which can be used to animate this. And you can see that after 2 or 3 rotations, the ball's in the center, goes through sequence of contact and non-contact. And I'm happy to make this Modelica code available to anybody who would like to play with this problem. So the real problem we're after is this soft touch robotic control. I don't have a lot of time left, so I'll go through this quickly. Essentially, we have a delta robot that's modeled as a set of DAEs that's represented in Dymola. The feedback controller here are all represented in discrete time. As I said earlier, you can't compute the forward kinematics in closed form, so that's computed numerically. We include the physics of what we're trying to manipulate, which is in this case a Lego brick. And the interaction here is captured using this model that we've already talked about here. And so here's just a simple simulation result where we're moving the robot here towards this block. As we get close, we reduce the velocity. And as we get even closer, we reduce the KP gain in this outer loop PD control all the way to 0 so that we get very low impedance during the contact and very soft contact force. And so here you can see the Lagrange multiplier. We have contact with this object. The contact state goes to 1. And actually this force is very, very small, which we want for this particular application. So here we want a simple unified model of both the part we're picking up and the robot so we can design these types of controllers and, of course, simulate them. So thank you very much. I'm all finished. Basically, this is a hybrid differential algebraic equation finite state model of the rigid body contact and collisions that is useful for both robotics and those other problems I spoke about earlier. Importantly, we want to use this model for more than just simulation. We want to use it for model-based control design. The implementation is completely in native Modelica. I think this is probably useful for very limited types of problems, so low dimension with a little bit of damping. One caveat, this is critically dependent on event detection, and I've seen failures in the standard tools that we use for Modelica, and so because this is an event-based method. And so this can fail if the event detection actually fails. And like I said earlier, I'm happy to make the code available if people are interested. Thank you very much.